Hello everyone and welcome to Math 163, the revised version of Calculus 3. What we are starting today, phase 1 of the class, is a discussion of what are called Taylor polynomials and Taylor series. Taylor polynomials are going to be an extension of the idea of the tangent line, the linear approximation to a function. So as we get started on talking about Taylor polynomials, let's start with a review of linear approximation from Calculus 1. The linear approximation to a function f of x, calculated at x equals a, was the line that had the following two properties. First of all, the slope of the line was given by f prime, the derivative of the function evaluated at the relevant x value. And second of all, the line touches the graph of the original function at x equals a, or put another way, in other words, the line passes through the point in two-dimensional space where the x-coordinate is equal to the a value at which you're doing the calculation, and the y-coordinate is a match to the output of the original function at that specific value of a. So the linear approximation to a function, also known as its tangent line, was the line with the following two properties. The slope of the line is equal to the value of the derivative, and the line passes through the point xy, the x value being the a that you're using in the calculation, the specific value that you're using in the calculation, and the y value being the output of the original function at that same point. Now, if you know the slope of a line, and if you know a point that the line passes through, you can use the point slope formula for a line to find the line's equation. So let's just remind ourselves that if you use the point slope formula for a line, if I apply this point slope formula to specifically the tangent line described in this paragraph, the slope of the line is going to be f prime at a, so that's going to be our m value, the slope of the line. And the specific point that the line passes through is going to be given by a comma f of a. This is going to be what the point slope formula calls x naught, y naught. We'll replace the m by f prime. We'll replace the x naught in the brackets by a, and we'll replace the y naught in the back by the output of the original function evaluated at a. So this is the formula for the tangent line. This is the formula for the linear approximation for the function f of x. Now let's go ahead and do a calculation of the linear approximation for a specific function at a specific x value. Here, for example, we are asked to find the linear approximation for f of x equals the square root of x, calculated at x equals 4 specifically. Then let's compare the graph of the original function, the square root, to the graph of its linear approximation, that tangent line. Okay, so to find the linear approximation for a function, we need to be able to fill in all the blanks and all the gaps in the linear approximation formula. So first of all, let's acknowledge that we were given the value of a in this paragraph. The value of a is the specific x value at which the linear approximation is calculated. So in this case, since we're calculating the linear approximation at x equals 4, 4 would be the value of a in this problem. So now that I know the value of a, I can also try and find the value of the original function f evaluated at a. So f of a would be f evaluated at 4. Our function in this problem is the square root of x. So f of 4 would be the square root of 4. And so that square root of 4, that 2, would be the value of f of a in the tangent line formula. Now the last gap that we need to fill in is the slope of the tangent line, the slope of the linear approximation, which would be given to us by plugging the a value, plugging 4 into the derivative of the function that we're working with. So in order to be able to do that, I need to find the function's derivative first. So I'm going to go ahead and find f prime of a. I'm going to go ahead and find f prime of x first, using, for example, the power rule on this square root function. Because I remember that the square root of x is equivalent to x to the power 1/2. So if I apply power rule to that quantity, the exponent will come down 1/2 in the front, and then I will decrease the exponent by 1 unit. So 1/2 minus 1 giving me -1/2. This would be the formula for the derivative of the function in this problem. So now I'll go ahead and plug my specific value of a into this formula. Plug specifically a equals 4 into this formula. 1/4 from that calculation. So we're almost done. We have now found the values of a, f prime of a, and f of a in the linear approximation formula. So now all I have to do is go into this expression and fill in those blanks with these specific values that we've calculated. Y equals the slope of the tangent line, the output of the derivative, which we found was 1/4, then multiplied by the quantity x minus a, in our problem x minus 4, and then adding on to that the output of the original function, f of a, so adding on to that 2 to that expression. So notice something really important. When you're finding the equation of the tangent line to a function, in other words, when you're finding a linear approximation for a function, the linear approximation should, at the end of the day, be a line. The linear approximation should be able to be written in the format mx plus b, number times x plus another number, because that's the standard format of the equation for a line. If you're getting anything other than the equation for a line when you're doing a linear approximation, that's a sign that you've done something wrong somewhere in the calculation. And what I often find that students do wrong most often is that they forget to plug in the specific value of a either to the original function or to the derivative of the original function. The most common error I see from students is just to take like f prime of x and plug that into the equation, but we're not able to do that. We have to do f prime evaluated at this specific x value that we are given in the problem, the value that the linear approximation is calculated at. So now that we have found the linear approximation for this function at this specific x value, let's go ahead and follow through with the second part of this problem, comparing the graph of the original function to the graph of its linear approximation. Okay, here we are on Desmos. In red, we have the graph of the original square root function, f of x equals square root of x. And in blue, we have the graph of the linear approximation to that function, calculated at x equals 4. And then in green, I've marked the specific point on the graph of the function where x is equal to 4. So that's right over here in this picture. So what I want you to notice about the relationship between the graph of the original function and the graph of the linear approximation is that if you look at the two equations in the vicinity of x equals 4, the linear approximation and the original function are extremely close to one another. We can see, even as we continue to zoom in, that the linear approximation in blue and the original approximation in red are so close together that they seem almost to overlap as we get closer and closer to this location x equals 4, where the linear approximation was calculated. This is why the linear approximation is called the linear approximation, because the linear function in blue approximates. It is very close to the original function here in red. And that is the real advantage of the linear approximation. The linear approximation is typically a very simple function. Linear equations are very simple, very easy to work with. The linear approximation is a very simple function that is very close to the original function. So the linear approximation can often be used in place of the original function to increase the simplicity of your calculations while introducing just a very small amount of error into the calculation. And so I've summarized that here. Because the linear approximation is so close to the original function, and because the linear approximation is often much simpler than the original function, it's sometimes useful to replace a function by one of its linear approximations, especially if estimate answers are permitted. So in order to demonstrate that idea, replacing a function by its linear approximation to make a calculation easier, let's consider the following problem. Here we're asked to estimate, so notice this keyword estimate. Estimate the integral from negative 0.2 to positive 0.1 of the function cosine of x squared. Now, normally in Calculus 2, when you're given a definite integral, the normal thing you do to calculate definite integrals is to find an antiderivative of the function that you're integrating, plug the two limits into that antiderivative, and then subtract the two results. The issue with doing this integral normally is that cosine of x squared does not have an antiderivative that we can find using any of our normal tricks. So instead of calculating this antiderivative normally and integrating normally, I'm going to take advantage of the fact that this is only asking me to estimate the value of this definite integral. And if I'm asked just to estimate the value of this definite integral, that unlocks a couple of alternative methods that could be used to tackle this problem. The first way, of course, is to integrate numerically. In other words, to use, for example, a left or a right Riemann sum, or to use trapezoid rule if you learned trapezoid rule in Calculus 2. And that's fine. That'll get you an estimate. You can choose your delta x, you can build your table, you can use the Riemann sum formula, etc., etc. That'll absolutely work here as one way to estimate this result. The second way to estimate this result is to replace cosine of x squared with a linear approximation. The idea being that the linear approximation will be close to the original function, but the linear approximation will be much, much easier to actually integrate. If we replace cosine of x with a linear approximation, then we will be able to integrate that linear approximation normally. So I'm going to go forward with option number 2, just because that's what this lesson is all about. And I'm going to go ahead and calculate a linear approximation for cosine of x squared. Well, in order to find a linear approximation, I need a value of a. I need a value at which the linear approximation is going to be calculated. If I don't have a value of a, then I don't have enough information to fill in this blank in the formula, or this blank in the formula, or this blank in the formula. Now, in some problems, I'm given the value of a explicitly. Like here it said, I want to calculate the linear approximation at x equals 4. So 4 was given to me as the value of a for that problem. However, in this problem, I'm not given a specific value of a. So I'm going to have to choose a suitable value of a myself. So as I'm working on choosing a specific value of a, let me remind myself that in the graph, the linear approximation and the original function are very close to each other near a. If you're operating near the value of a, that is where the linear approximation and the original function are very, very close. Now I'm looking at my problem, and my problem is dealing with input values on the interval from negative 0.02 up to 0.01. Now, what I notice about all of these x values is that they are all very close to a specific value x equals 0. So what I think I'll do is I will choose to calculate my linear approximation at x equals 0, because that's a very simple x value that is very close to the x's that I am working with in my problem. So now that I've chosen my value of a for the linear approximation, let's go ahead and find that linear approximation. We've already chosen a equals 0. So now if I plug that a value into the function that I'm working with in this problem, the function cosine of x squared, f of 0, cosine of 0 squared, is going to be equal to 1 unit, just a simple 1 unit. Then I'm going to need to find the derivative of this function, f prime. And using the chain rule, that's going to be equal to negative sine of x squared multiplied by the derivative of the inner function. And if I plug 0 into that, I get negative 2 times 0 times sine of 0 squared, which works out to be 0 in the end. So my linear approximation is going to have the formula: the slope of the tangent line, the output of the derivative, which we found is 0 in this problem, times x minus a, where we chose a equals 0 in this problem, and then plus the output of the original function 1, the output of the original function 1 in this problem. Now that linear approximation is going to be very, very close to our original function, cosine of x squared, for all the x values that are relevant in this problem. So that means that instead of integrating cosine of x squared from negative 0.2 to positive 0.1, I can get an answer that's approximately the same by integrating the linear approximation instead. And that linear approximation is way, way simple compared to the original function, right? To integrate 1, all you have to do there is find the antiderivative x and then plug in the two x values on the limits. And so we find that the value of this integral is approximately equal to 0.03 units. That would be my estimate, my quick estimate for the value of this integral. Let's compare this result with what we would get using, for example, computer assistance to calculate this definite integral that we were given. So here I am, for example, on Wolfram alpha, and I am integrating cosine of x squared from negative 0.02 to positive 0.01. And Wolfram alpha says, hey, the result approximately equal to 0.03, right? Which is exactly the same as we estimated over here by replacing cosine of x squared by one of its linear approximations. So we've gotten quite an accurate result here, but we didn't have to do a Riemann sum, we didn't have to do the table, we didn't have to choose a step size. The linear approximation gives us an alternative way to get that result. So now let's spend a little bit of time extending this idea and bringing in some new ideas for Calculus 3. So we've just done the linear approximation and we've just done the tangent line to a function. So one might ask, what if instead of approximating the function using a line, what if we approximated the function using a quadratic or a cubic, for example? Polynomials like that, like quadratics, are also very simple to work with from a calculus perspective. Like you can still integrate quadratic functions very, very easily. So maybe it's useful to approximate functions that are heavily curved using polynomials, using quadratics, for example, which are also curved. The formula for the Taylor polynomial approximation for a function is a very natural extension of the formula for the linear approximation. In the linear approximation, we had the output of the original function, and then combined with that, we had the output of the first derivative times x minus a to the first power. Now, if you want to do the Taylor polynomial, you extend that pattern. If you want to approximate using a quadratic, using a polynomial of degree 2, the formula for that is take the output of your original function and then take the output of the first derivative times one copy of x minus a, and then the output of the second derivative times x minus a to the second power, and then this one's a little unexpected, divided by 2. If you want to do the cubic Taylor polynomial, if you want to do degree 3, you take the output of the original function, you add on to that the output of the first derivative times one copy of x minus a, you add on the output of the second derivative times two copies of x minus a over 2, and then the output of the third derivative times 3 copies of x minus a, and then this one's a little unexpected, 3 times 2 is what you're dividing by. In general, if you want to approximate a function using a polynomial of degree n, the formula for that is given by the sum So I'm about to use summation notation from Calculus 2. The sum, as k goes from 0 up to n, of the kth derivative of the function evaluated at a times k copies of x minus a divided by something called k factorial, denoted here by k with an exclamation mark next to it. If you've never seen the factorial before, if you've never seen this notation, this exclamation point for factorial has the following meaning. If you want, for example, to calculate 5 factorial, then you count down from 5 all the way to 1. 5, 4, 3, 2, 1. And then you multiply all those numbers together. 5 times 4 times 3 times 2, that's what, 120? If you want to calculate, for example, 3 factorial, that's 3 times 2 times 1, that's 6. 2 factorial would be 2 times 1, that's 2. 1 factorial is just 1. And then we just agree that 0 factorial is going to be 1 as well. And this is just convention / agreement. So this factorial here in this denominator is capturing the fact that here underneath the second derivative is 2 factorial just being 2. Here underneath this third derivative is 3 factorial, 3 times 2, giving us 6. Here underneath this first derivative is 1 factorial, which is just 1. And here underneath, no derivatives is 0 factorial, which is also 1. You just cannot see the divided ones because dividing by 1 doesn't have any effect. So let's get some practice calculating some Taylor polynomials, for example, for the function sine of x, calculated specifically at a value of 0. And we'll calculate these Taylor polynomials for degree 1, 2, 3, 4, and 5. And we'll compare those graphs to the graph of the original sine function. So first off, to calculate these Taylor polynomials, the Taylor polynomial formula requires that we have the derivatives of the function that we are approximating. If, for example, we want a 5th degree Taylor polynomial, we would need to calculate up to the 5th derivative of our function. So let's line those up. If the original function is sine of x, then the first derivative would be cosine of x. The second derivative would be negative sine of x. The third derivative would be negative cosine. And then the fourth derivative would be back to sine. And then the fifth derivative would be back to cosine. Now, in this problem, our Taylor polynomials are said to be centered at 0. Centered at 0. So when we're saying where the polynomials are at, this is pointing us toward the value of a. The quantity referred to as a in the Taylor polynomial formula / in the linear approximation formula. So let's go ahead and plug a equals 0 into each of these functions to find the specific values that would go into the Taylor polynomial formulas here. So if f of x is sine, then f of 0 is 0. Cosine will output 1. Negative sine will output 0. Negative cosine will output -1. Sine will output 0. And cosine will output 1 again. So now let's use these values to build all the different Taylor polynomial approximations to the function sine of x. So the Taylor polynomial of degree 1 is just the same thing as the linear approximation. You can build it by taking the output of the original function and then taking the output of the first derivative and multiplying it by one copy of x minus 0. So this simplifies just to x. The degree 2 Taylor polynomial would be the exact same thing, but with one additional term. The output of the second derivative divided by 2 factorial times 2 copies of x minus 0. So once again, that'll simplify just to x. The third degree Taylor polynomial is the same thing as the second degree Taylor polynomial with just one extra term. The output of the third derivative, here minus 1, divided by 3 factorial times 3 copies of x minus a. So after simplification, this becomes x minus x cubed over 3 factorial. And let's go ahead with the fourth degree Taylor polynomial. I'm just going to go ahead and copy paste the third degree Taylor polynomial and then add on just one additional term. The output of the fourth derivative of our function divided by 4 factorial times 4 copies of x minus 0. And then finally, the last one, the fifth degree Taylor polynomial. I'm going to go ahead and grab the fourth degree one, and then the fifth degree Taylor polynomial will just have one extra term attached. The final term being the output of the fifth derivative, which is 1, divided by 5 factorial times 5 copies of x minus 0. So this will simplify. I'm running out of space here. This will simplify in the end. Once we cancel all the zeros and such, this will simplify to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So these 5 polynomials of degree 1, 2, 3, 4, 5 are different Taylor polynomials that serve as approximations to the original function sine of x. Now let's go ahead and look at these Taylor polynomials on a graph and compare those polynomials to the graph of the original function sine. Okay, so here I am on Desmos with y equals sine of x graphed, and I'm looking at the point on the graph where x is equal to 0, because 0 was where the Taylor polynomial was centered in our problem. 0 was the value of a in our problem. Now I'm going to go ahead and graph y equals x. Y equals x was the first and the second degree Taylor polynomial for this function at this a value. And what we can see is, just like the linear approximation, because this is the linear approximation, this function in black hugs very closely to the sine function for x values that are relatively close to the center, x equals 0 in this problem. But as you begin to move away from that center, as you start dealing with x's that are further away, like x equals minus 1, x equals positive 1, we can see a pretty noticeable discrepancy and gap between the original function and the linear approximation. So let's see what happens if we crank up the degree of the approximation and we graph the Taylor polynomial of degree 3. So that was x minus x cubed divided by 3 factorial. So the Taylor polynomial of degree 3, we see here in this picture in blue now. And so what we can see is that compared to the linear approximation, which very noticeably broke away from the original function around x equals 1, the Taylor polynomial of degree 3 approximates sine of x much more effectively for a longer period of time. Because sine of x is curved, and because the cubic functions are also curved, the cubic function is able to stick closer to sine of x for a longer period of time. Even over here at x equals 1, the Taylor polynomial and the sine of x function are very close to one another, very much overlapping on this graph. So the Taylor polynomial of degree 3 is a better estimate for a longer period of time than the linear approximation. But we can see a discrepancy beginning to form over here at x equals 1.5, right? Here where the two functions are beginning to separate from one another. So let's see what happens if we graph the Taylor polynomial of degree 5. Okay, so now the Taylor polynomial of degree 5 is this one drawn here in green. And that's this one here, this one here. And what we can see now is that the Taylor polynomial of degree 5 hugs close to sine of x for an even longer period of time, right? The Taylor polynomial of degree 3 began to separate from sine of x as early as x equals 1.5. But if I allow myself the Taylor polynomial of a higher degree, then that degree 5 polynomial is still very close to sine of x, even as far out as x equals 1.5 or 1.6. And you only begin to see a gap between those two functions at around x equals 2. So to summarize what we've seen from the graph, as we increase the degree of the Taylor polynomial, two things happen. One, calculating the Taylor polynomial becomes a little bit more labor intensive. The higher the degree of the Taylor polynomial, the more derivatives we had to calculate, and the more complicated the formula that we needed to fill in and then simplify. However, as you increase the degree of the Taylor polynomial, what we also saw from the graph is that the higher the degree, as we moved from first degree to third degree to fifth degree, the Taylor polynomial became a more accurate approximation of the original function. So you can do everything with the Taylor polynomial that you could do with the linear approximation. If you need more accuracy in your calculations, all you have to do is crank up the degree of your Taylor polynomial, because the higher the degree, the more accurate your estimation becomes. The downside is, as you calculate the Taylor polynomial with higher and higher degrees, actually finding that Taylor polynomial takes more time and more labor.